Success in AP Physics will depend in part on your fluency with the concept of energy, and gravitational potential energy is by far the most common you'll run into. So we're going to spend some time just going through some different applications and implications of what we just talked about. So these are basically just a series of gravitational potential energy problems. Starting from rest, a marble first rolls down a steeper hill and then down a less steep hill of the same height. For which of them is it going faster at the bottom? Is it faster at the bottom of the steeper hill, faster at the bottom of the less steep hill, the same speed at the bottom of both hills, or you can't say without knowing the mass of the marble? Well, all of the gravitational energy at the start is going to end up being kinetic energy at the bottom. And the marble starts at the same kinetic energy in both cases because it starts with the same height. And that's all that matters, not the horizontal part, but just the vertical part. So in both cases, they have the same kinetic energy at the bottom, which means in both cases, they have the same speed. Notice you don't need to know the mass of the marble. It will scale the potential energies, but it's always true that a higher height is going to be more potential energy. It's always true that a faster thing is going to have more kinetic energy. It doesn't matter what the value of the m is if you're just comparing greater than or less. So what if the marble in the steeper hill was twice as massive as the other marble? So what if we had that this was 2m and this was m? Well, if we look here, we'd say, let's just take the guy on the right, and we would say that energy at the start, right? All of the potential energy becomes kinetic energy. So mgh becomes 1/2 mv squared, which means that vgh becomes v squared, and the m has dropped out. So it doesn't matter if it had been twice as much. So it's the same speed at the bottom both. Which ball is going fastest at the bottom of the track? And there are 4 different tracks shown, which are roughly in fact, I think are in the order shown here. So we have, actually, I think it's D, C, B, A. And hopefully at this point you're starting to realize it's going to be the same for all of them because the height is the same. So let's watch and see. It's done in slow motion. So don't be fooled by the fact that they reached at different times. That wasn't what was asked. It was which is going faster or not, and they're all going at the same speed. From the video, how can you tell they're going the same speed? Well, let's watch it again. I want to keep an eye on the spacing between balls A, B, and C. D comes too late for you to see it. Do you see how the spacing doesn't ever change? Once they reach the bottom part, they are covering the same ground in the same amount of time on the floor, and so therefore they have the same speed. Just because that was a lot going on, this is a somewhat cleaner version of the same thing.
One of the best energy demos is this Racing Marbles lab. 2 marbles are released from the same height and race along different paths. But which one will reach the finish first? Make your guess and tell the person next to you why you think you're right. Alright, here we go. 3, 2, 1... Now that you have seen the result, explain it correctly. The marble that was allowed to dip lower got to convert its potential energy into kinetic energy, which let it go faster. The higher marble moved at pretty much the same constant speed. By the end of the race, they do both finish at the same speed, just not at the same time.
And again, you could see they had the same speed because they keep a constant distance once they're back on the straightaway. All right. Hockey puck sliding on smooth ice at 4 meters per second comes from a 1 meter high hill. Will it make it to the top of the hill? Yes, no. Can't answer without knowing the mass of the puck. Can't know without knowing the angle of the hill. One way to tackle this is, let's find the final kinetic energy, assuming the puck does make it up the hill. So we'll make the assumption, see if it's true. So we say the kinetic energy at the end is whatever it had at the start, plus however much it changed by. And so when we grind out some numbers, we find the kinetic energy at the end would have to be minus 1.8 meters per second squared. In other words, it needs to gain more gravitational energy than it starts in potential with kinetic energy. Kinetic energy can't be negative, so the situation isn't possible. It doesn't make it up the hill. You could also say, hey, how high could it go? In other words, convert the initial kinetic energy into mgh. What would h be? You find it's only 0.881, so it's not enough to get up the hill. Either way, it doesn't make it. And that's what I was saying earlier, where if you get a negative kinetic energy, it can tell you not that you're wrong, but that your situation can't be what you thought it was. 3 balls are thrown from a cliff with the same speed but at different angles. Which ball has the greatest speed just before it hits the ground? This is almost a trick question because they start with the same kinetic energy and they fall through the same height. So they're going to gain the same, they're going to give up the same gravitational energy and increase the kinetic energy by the same amount. So they're going to have the same speed. Small child slides down the 4 frictionless slides as shown. Rank in order from largest to smallest for speeds at the bottom. Okay, by now it's probably no surprise at all, and you're probably getting a little tired of it, but it doesn't matter how their track is or how long it takes to get there or how far they have to travel. All that matters is the height. The height's the same, so therefore the velocities are the same.